Hi. So I want to try something new. I haven't really recorded anything before, but was thinking about if there's a subject about programming that's really changed the way I think about data and think about computing and working with software. What would I share? And what do I think is worth teaching and worth learning? And the biggest idea that's really come to mind has been streams. And if you've ever worked with me in a professional capacity, you probably already know that I'm obsessed with streams and usually can find some way to turn most problems into stream problems. So what I hoped to do today was kind of walk through a couple of ideas and just kind of keep it short. There's more things I'd like to add to this discussion, but really what I want to be able to do is think about how to show you why streams are useful, what problems they solve, when you might want to think about, can I turn this problem into a streams problem? And I also want to show you that streams is a concept. Before we gave it a name, that concept already existed. So how it manifests itself is usually what most people learn. And I think most people have probably heard about streams in the context of something like I/O, which would mean data coming out of a hard disk or out of an SSD, out of a file into your program, or out of your program to a file. Or sometimes you might have heard about I/O in the context of HTTP, or sending data from a web server or downloading data from a web server. And in that, you can think of those data as streams, and we're already quite comfortable thinking of streams that way. But what I thought might be interesting is introducing streams in a different context that doesn't have to do with I/O, but showing that we can express these problems as stream consumption problems, and showing you how we could do that, particularly within Node. There's other languages I'd like to show how you can think about a problem as a streams problem and express it. Go is probably one that comes to mind. But for now, we're going to start with Node. It's what I spend most of my time working on professionally, and JavaScript it's got a few aspects to it that make it quite natural to express a problem as a streams problem. So enough of that, we'll dive in. So first, let's start with the problem. And I want to speak to this whether you're a Node programmer or even a JavaScript programmer, or whether you're not a programmer at all. I'd like to try to do my best to explain concepts in a way that can be at least understood, even if you don't work with programming, but you understand logic or math concepts. Some of this might be tedious to folks who already know all these concepts, but I do want to try to make this accessible to a few different people. So let's start with how we would introduce or model what we call the Fibonacci program, right? And so Fibonacci is a way of expressing a number sequence where each number is the addition of the two numbers before it. So when I have 3, the next number would be 2 and 3, so I would get 5, and then 3 and 5 gives me 8. So let's write a function that can do that. And again, if this is your first time ever looking at JavaScript, this would be new, so I'll try to explain as I go. So we're going to declare a function, and a function is something that takes in 0, 1, or more arguments, and produces a response or a result from it. So if I give something called fib, and the Fibonacci function is going to give me, if I ask it for a certain number of elements, it's going to return to me a list of numbers with that many elements inside. So let's just start by giving it those numbers, so const. This is just how I declare a holder for things, and I'll return those numbers when I'm done. So let's do it this way, where if I say let A and B be some holders for some numbers. And for now, let's make them 0 and 1. So if I want to make a list of that many elements, I'll say while my elements number is greater than 0, and let's just make it obvious that this is a number. So while it's greater than 0, we're gonna basically kind of count down until we run out of elements, until this is 0. So this is one way to loop through it procedurally. So while I have that, I want to push in my numbers. So I'm going to say const C is going to be the next number in line is going to be the result of A and B, and then we're going to say that A is going to equal to B, and B is going to be equal to C to move those two into the next positions for the next run through. And then we'll push C into nums. So we'll take nums, and I can say, please push this into that list, and that will give me C. And then that will decrement So if I ask for 10 elements, then it's going to say do this again, but I'm only looking for 9 more elements. And then when I run out of that, I should return the numbers. So the way that we'll check this is I can run this program against fib. But first I have to ask it to print it out. So if you've never seen programming before, when I do console log, that's a function that will let me print information out to the system. So if I ask for the first 10 numbers, I should get a list printed out. 1, 2, 3, 5, 8, 13, 21. Now the formal Fibonacci list actually is supposed to start with 0 and 1, right? So let's just shove 1 in there just to start. And we've gotten that far, and that's enough for me to take a drink. So from there, I want to show you why this is a problem. So with a programming environment like Node, or really any other programming environment for that matter, the computer has in its in the computer it has memory, right? And so memory is different from like how many songs you can fit on your hard drive. This is how much brain power, I guess, how many things it can fit into its mind as it's working through a problem. And of course, my computer's got some number of gigabytes of memory, but any given program, we can't let one program take up all the memory. And so most runtime environments will have a limit on how much memory can be allocated to any one program. So when I ask for a number of 10 things, right, like let's look at some, this takes memory, this line here, this takes some memory, and those are 2 pieces of memory that are reserved for holding onto those counters. This here is actually going to hold on to memory, and this is a list of numbers, so somewhere it has to compute, the computer has to make a temporary holder for a list of numbers that we're going to continue adding to. And so within this little program, 10 numbers is just trivial to put these together. But what if I ask for 1,000 numbers? Well, that's not too much harder to do, right? So let's run that again. And we're going to be doing this over and over and over again. Here in the second window, I've got, basically I can run the file that we're working on right now. There's a little shortcut that I can use. So I'm going to borrow from my, this is my configuration that I use in my editor. So I'm going to set up a little command just for this, this tutorial. So I'm going to ask my program tmux to send some keystrokes. And this is called streams. And I'm going to say that the window on the right there is called 0.1. Control L means clear the screen. Control P means bring up the last command. Control J will submit the command, and then that submits it, and Node is going to, or rather Vim is going to ask me to confirm the output, and I just want to clear it that way. So let's do that. So if I run /r, that should run the last program over there. So that's how you're going to see me using that quite a bit. And if you don't see why the thing on the right is going, that's because I'm running that key command. So I have that up and running. So 1,000 is fine for the computer. How about 1 million? That seems fine too. But if I take it up to 1 billion, I should expect this to blow up. Let's do one more. All right, eventually I blow up. So let's focus in on here. So this does not look normal. I've got last few GCs, and that means garbage collections. I've got allocation failure. Again, so the program node is, when I have an allocator, it's basically I'm asking for more memory. It's going to find some free memory, assign the things that I want into it. It's making space for me to do the work as I'm doing it, right? So this is a problem because eventually I get to this error, invalid array length allocation failed, JavaScript heap out of memory. And every time I push something in, that memory space, that list of numbers didn't fit in whatever space it was before. So it's got to find a new place for this list that's longer by 1 and add it there. And eventually I run out of memory. And this is a problem that can exist in a program like this. It can exist if you've ever tried to open Excel with a file that's way too big, or if you have, if you've ever worked in web programming and try to process a file that's too large. Anytime that you try to get all of your data in one place in memory so that you can work on it, you potentially run the risk of running out of available memory. So you can solve that by getting a bigger computer, or you can solve that by not requiring yourself to have all of the data in place at one time before you can work on it. So rather than, in this case, what we want to be able to do with these numbers is put them all in one place so we can print them out. What if we could process each piece of data as it comes through? So instead of waiting until the last number comes together, can we start working with the data when the first number shows up? And then when the second number shows up, we do something else with it. And in this case, we're just printing it, right? So we could rearrange our problem, and we'll introduce a little for loop here. So if I say for, and then again, if I use const or let, I'm just declaring a name for where I want to store something. So for each number of my list, so I'll say fib of whatever number this ended up being, console.log, the number. So right now what I should be doing is walking through each number in my output and printing it out. Does that help? Well, we can find out, we can be curious, and we can see, and it doesn't help. So the reason for this, and this is the way that JavaScript and a lot of other programming languages work, especially when they're strictly evaluated, means it's going to actually run this and get the answer and put it here in that highlighted region before the rest of the loop gets to run. So it's going to basically go from inside out, and it says, well, I have to evaluate all of this before I can evaluate all of this. That's strict evaluation. There are some languages, Haskell comes to mind, that are lazily evaluated. And what that means is Haskell's not going to do work until it knows that it absolutely has to. And then Haskell might not even immediately solve this as written, but the idea is most languages by default, unless they intentionally do this, are going to try to evaluate everything, put it in place in one place before it lets you move on and work on it. So that is our problem, and that's where I want to start getting you thinking that Streams is not strictly about I/O. It's not strictly about files or web requests. It's about data, and it's a strategy to handle or process your data in a fashion that you don't have to wait for all of it to be in one place before you can start working on it. And in fact, if you're able to think of your data as a stream or just a linear ordered sequence of pieces of data that you can start touching as they come through, that's called streams. So let's rewrite this as a streams problem and see if we can make a thing, get more work out of here. So what's going on with fib here is that we're accumulating all of our results into this nums variable and returning it when it's done. Instead, what would be nice is if we could start emitting values as they come up, such that we can start sending the results, pieces of the results, bit by bit as they're calculated, as opposed to waiting for the end. And JavaScript does have a tool that lets us do that. And those are called generators. I don't use them a ton for work, but every once in a while they are quite handy. So this little asterisk right here basically means I want a function, but that's actually a generator. And a generator has a key word in it, a very special word or operator called yield that lets me return a piece of my result before the whole result is finished. So if I call this fib generator, so fibgen, we'll do it the same way. Again, we'll say that if you don't give me elements, it's going to default to 0. And we basically can write the same problem. So let a equals 0, let b equals 1. And then while I still have elements, and again, a lot of this is going to be the same. Same little algorithm. Basically, I calculate the next number in the sequence. I update my little placeholders. And instead of pushing, right, because I'm not accumulating a result, I'm emitting a result, I will yield C to whoever my caller is. And then I will do this. And so basically, this will continue yielding and spitting out results while I still have elements to calculate. And then that will be done, right? So what I ought to be able to do then is iterate my generator. Now there is one silly little trick here. I'll show you first how that works. So what I'll say is for const num of fib, and let's just do something small for now. So fibgen is going to create a generator And JavaScript knows how to consume these generators and walk through them. So let's comment this out because we don't want to actually run this because we know that that breaks our program. So let's give us some room to bring this back up to the top here. So I've got my generator. Let's walk each one and print it out. So over here you can see I've got 1, 2, 3, 5. Yeah, that still looks right. And we're still missing that pesky first number, so we'll just yield it before we actually start looping through everything. And then I've got proper Fibonacci 1, 1, 2, 3, 5, 8. So the generator is letting us basically emit data and consume it as it's being calculated instead of waiting for the end. So this is our first taste of moving toward a world where we're starting to think in a streams producing and consuming fashion. This still isn't totally streams, but the ideas are there. Streams are a first-class citizen inside of Node, and it does have some facilities for working with streams as streams, and it has special tooling and special extra things that you can use that we can just pull out of the box, right? So let's move on to that. So let's rewrite this with a formal stream. So if we come over and look at the Node documentation for streams, this is worth just sitting and reading someday and taking your time. Because Node came out, and I remember when it came on the scene back when it was still like version 0, it came with a few really powerful ideas, and callbacks are the ones that I think everyone kind of ended up latching on to. The whole asynchronous single-threaded loop and the event loop and working with that. That was a new way to think about programming. It was really powerful and unleashed a lot of things. But Node initially launched with this notion of events and reacting to events. And in fact, the event loop itself, most of the time they're handled with callbacks, but the notion of just the events and reacting to them has always been a part of Node. It's been a part of JavaScript for a long time. Especially for those of us that have maybe started doing browser programming where like a click or a user typing, those are events that you respond to. Here we've got this big table of contents, and there's a few classes, or you can think of them as just pre-packaged bits of code and behavior. There's a writable stream class in here. There's a readable stream, and in fact these are a concept, and then there's an implementation of these streams, and it even mentions that there's an API style. So you can think of an API as just how you work with something, like what behaviors it exposes and what contracts it guarantees. And if you give me these things, I will guarantee you that you will get these things back. So we've got some interesting things I want to draw your attention to, like pipe. I think I'll want to do a video later about just how Unix or Linux-based systems deal with pipes. That's a really strong notion that lives inside your computer. And Node has that built in as well. Those idioms are the same whether you're working inside of Node or in Linux. And there's just different things that a readable stream ought to be able to do. And really it kind of reads like English. Like a readable stream is something that you can read from, which assumes to mean that like it will be producing content for you to consume. And you can keep consuming it until it tells you, I'm done. I don't have any more things to work with. It shows here this is the event-based way of working with the stream, that it will emit something called a data event, and it will pass a chunk, and then you can do something with that chunk. And the reason that they're called chunks, and again, this kind of comes back to just how web servers and files-based systems communicate and talk to each other, where it's gonna have a little buffer in memory, so it's a fixed length place or array, a placeholder maybe, where it's like, I'm going to fill this up and then I'm going to shoot it out, and then I'm going to fill it up with the next bit and then I'm going to shoot it out. Those bits are called chunks, and it sends those out, and you react to those chunks on the other side. So you kind of connect, here's the producer, and then you connect your consumer, and you start reading chunk by chunk, and then on the other side you can assemble them in whatever way makes sense to you. We can also think of chunks as just numbers, in our case, or bits of data, objects, that kind of thing, messages. Whatever makes sense for your problem, and if you can model it again as just a stream of pieces, by default, streams they're thought of as, basically the most abstract way to think about it is they're just bits of bytes, right? And a byte is like one of these atomic units that kind of make up a file or a request or a single sliver of a millisecond on a CD or an MP3, chunks. And they're in a line, and then you process them as you go. So these are basically how Node thinks about streams. There's a lot you can read in here. So we'll be working with this. There's a really nice syntax for how to implement your own readables. And let's go back up to the table of contents, see if I can find it a little faster. API for stream implementers. We want to implement a stream. Implementing a readable stream. Let's go into that. So there's a couple different ways we can go about it, but this one here looks the easiest and it's probably the easiest to set up. So let's do that in our program. So up at the top, with Node we can bring in other libraries, other pre-programmed bits of packages of code and behavior. So I want to import and extract from that import the readable class. So great. So down here, don't mind all the other underlines. I haven't configured this out of the box just to. It's not happy with my console logs and my requires because I haven't told it that I'm working with Node. So let's come down here and we're gonna make a new stream. So const. Let's just call this fib stream. So we want a function that will return a stream of Fibonacci numbers. So we're going to do the same thing with the elements. Let's just call this a function that will return a stream. So it looks like I can implement a few methods that the stream's API or the stream's contract or the standard agreement for how to work with a stream expects. So it expects return a new readable. And that readable has to at least have a read method because the thing that's reading the stream is going to call read on this. And when I say call read, it's going to say that's part of the API. It says like anyone that's trying to read from the stream or consume the stream is like, if I have this stream that I can talk to and interact with, if I tell it, give me .read or send the read message to it, or the read command, you can think of it that way, it will behave a certain way. It will bring back a chunk to me. Right? And then it takes with it a size variable, and it should return something, right? Okay, so we want to re-implement then our Fibonacci sequence with that. So the way that we'll say it is, got elements up there. Let's do our same thing of holding our little placeholder. So if I got A equals 0, and let B equals 1, and what I'm going to do then is every time it asks for a new number, a new Fibonacci number, I'm going to do that same little algorithm. C equals A plus B, and then A is going to equal B, and B is going to equal C. And then what I want to be able to do is write this to the stream. So because I'm implementing a stream class, I have something called push, right? And so basically I'm pushing into the readable. And this is like a little internal method, which is going to allow me to push the number onto the stream. So push C. Now, however, my stream eventually should have an end, right? So how do I know when this is ended, or more specifically, how do I convey that this stream is out of stuff? Well, if elements is equal to 0, I can quit. So what I'll do is I'll push null. And if I just return early like this, that's how I tell the program don't continue on after that line. So if I'm out of stuff, push the null, which that's an object that signals that the stream is out of things. And I can also, I'm not using size, so I can also just remove it, or I can tell my linter that size is actually not going to be used in this program. So let's just get rid of it that way, actually. Good, so I've got that, I've got pushing that. So how do I work with the stream? Well, I can make an instance of this stream and say fib stream. Let's do 10 items, and then let's log it, print it out to the screen to see what we're looking at. So as you can see, Node here is telling me the thing that you asked me to print is an instance of a readable class. It has a state, whether it's readable, whether it's started, whether it's how much stuff it has inside of it. There's something in here called high watermark. We'll discuss that, I think, in another day. But yeah, I have a stream here. I just can't do anything with it. I need to consume this stream so that, right now the stream is just sitting there saying, I represent a sequence of data. I represent more data, but because you haven't asked me for anything, I'm not going to give you anything. And that's the most important concept of streams. This is what makes them kind of lazy, which is to say, I won't give you anything until you ask for it. And that's a really important concept, because if you're on the other side, what if when I read that number, I'm going to do a lot of things on the other side, and it takes me like a couple seconds to do something with each number, or a minute to do something with each number. Maybe each number is another web request that goes and downloads a certain file with a name similar to that, and that takes a couple seconds. I might not be able to read your data as fast as you are able to produce it. And that's kind of where that high watermark comes into play there. I'll explain that some other time. But the whole point is here is I need to be able to communicate between my producers and my consumers. That also means that I need to have a consumer. So there was that first API, and again, this is like the old school way, and a lot of things have emerged since then that allow us to work with streams in a more streamlined fashion that's a bit more in line with how we expect to deal with other programs or how we write other programs. So it has an event called this data event, and I expect each thing to come out of it to be a number. So I can consume my stream this way. So now that there's a listener, Node is going to know, well, there's a listener, and it wants the numbers, so I should spit out the numbers. So let's see if that did anything for us. Invalid argtype chunk must be of type string, buffer, uint array, etc., etc. It received a number. So we got pretty close. Basically what it's telling us is, your stream's working, but I expected you to give me certain things. This chunk, I normally expect it to be bytes or string, which can represent some bytes. I expected this data to be simpler, and instead I got a number. That's what it's telling me. So let's fix that, right? Because I mean, it seems pretty limiting to only be able to work with strings or bytes. And technically, I bet I could fix it if I did this. If I just said turn each number into a string and then print that out. That sort of works, right? That's not what that doesn't make sense. I don't want that. So let's fix this. Instead, there's an option that I didn't use, which if we come back over here, again, sitting down and reading the docs is always a good idea. In here, there's some options that I can, so when I set up my stream, there's an object mode, whether this stream should behave as a stream of objects instead of just raw data like bytes or strings. Meaning that when you read something, it returns a single value instead of a buffer of size, blah, 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 blah. Well, let's try that. Let's see if it helps us out. So we want to turn object mode on in our stream, and then allow reading to work the way it did before. So infinity, which is not what we want, but at least it's not as mad. So let's see if we debug why our program is so pissed off. Excuse me. Infinity is not right. This is probably something that I will edit out, but for fun, maybe I won't edit it, and then you can see what it's like to work through these problems one at a time. Okay, so at some point, I realized my mistake. So scroll up high enough now. We saw that at the beginning, I don't know if you caught it, maybe I can slow it, stop it right, here we go. So we see like right now we have numbers before it gets to infinity, but if you see this little E sign, that means that we are really big numbers. Something happened, we're still going. Well, this thing doesn't know when to stop, that's the problem. So after I push on a new stream, let's decrement how many elements so that we know when to stop, right? Because this thing is still looking for elements to hit 0. And since we're not subtracting from the original number, it's never going to know when to stop. So now we've got numbers. Let's get rid of some of our console logs. So right here. That's just how you debug when you've been doing this for 10 years. All right, so we don't need to print out our stream anymore. Now we have our number again, right? So I'm not going to deal with that first time bit of why the leading one isn't there. We can solve it another way, but that's not the interesting part of this problem. So what we have now is a stream, right? And we're consuming the stream, but other ways to consume the stream. That's really what would be nice is if, because right now the thing that's consuming our stream is still inside of our program, so we're not talking to the outside world. There's a way that we can talk to the outside world. And so when I run console log, this is printing a message. Hello. It's printing a message to a default place, right? And over here on this side, we see that show up in the terminal. So this space in the terminal, by default, is called standard out. Standard out is just where normal messages go, and will feedback about your program. There's also something called standard error, which we don't need to talk about right now. But standard out is a writable stream in our world. From within my program, I can write to the standard out. That's a stream. It's a file. It's a stream. I'll explain someday why the terminal is actually a file. That's not the subject of this video, though. So instead, we can do some things where Node has the notion of piping in it. And if you're already familiar with working on the command line, you've probably used pipes without knowing it, or knowing that it was called a pipe. That's fine, but I'll show you what that character looks like in a second. So there's another way we can connect our readable stream, which is our Fibonacci sequence, to a stream consumer, or a writable stream. We want to connect these streams together. So process.standardout is how we communicate with the printing world, right? You can think of it as a printer, but instead of printing the paper, it prints to the terminal. And it says already here in my documentation that standard out is an instance of stream writable, so we should be able to connect our reader and our writer. So that is where stream.pipe comes in. So pipe takes a destination, stream.writable, and process.standardout happens to be a writable stream. So let's see what happens when we connect those. Chunk. Okay, so it's mad about that, which we can fix this really quickly, because again, we did do this object mode thing here, but process.standardout wants strings. And there is a more elegant way to think about this, but for now, let's just make it not mad. And that printed out. Now, there's something goofy here. You see 1, 2, this isn't actually one giant number, it's each number in our sequence, but instead of putting a new line in between, there is no new line. It's just printed out each number one next to each other. So there's ways to fix it. Really, what we would like to be able to, how we would like to be able to think about this problem, since we're thinking in streams now, we're thinking about each piece as it's going, and we're also piping it directly through. And so standard out doesn't know to put a new line character in between each character. So, or each number rather. So there is something we can do. There's a nice library. We can continue working with the streams directly as they are, but there is a really nice library that I love, and maybe I'll do another video just on this someday, called Highland. Highland is a way to make working with streams feel a lot more Node-like, or more JavaScript-like, I guess. In general, it brings a lot of the tools that we may have gotten used to in things like functional programming, or like if you've ever used something like Lodash or Underscore, these are other very popular JavaScript libraries for working with data. This is like that, but for strings. So it makes strings a lot more pleasant to work with. So we'll do this. Yarn, add, Highland, and now Highland is available inside our program. So if I want to work with a string in Highland, I can do this. I can wrap it, that string in Highland. Okay, so that doesn't give me a ton just right out the gate. Standard out. This should just work the way it did before. Okay. But I've got now, it gives me some tools that I can use before I send it on out to do standard out. So in between, we'll use something called map. Map is a transform function, if you haven't already ever heard of map. So if you remember in algebra, let's see if I can do algebra maps. Algebra maps. There's a nice little picture that explains let me see. Okay, so you can kind of remember this from math class maybe. I remember when I was learning math, I had to figure out, like, there's a function, or there's a way that you can go from the numbers on the left to the numbers on the right. Right, so here it's like, I don't know, 2n plus 1, does that fit for this? 2n plus 1 doesn't fit for that, doesn't fit for that. So there's, you would figure out, like, the arrow from the left to the right, we call these functions, or you can think of it as a formula for how to get from the thing on the left to the thing on the right. And this is something that we learned in math class, and maybe took it for granted, but I think that's the closest way for me to think of how to explain why map is called map. It's a way to take something on the left and transform it to a new thing on the right. And maps tend to work on lists of things. So if I've got a list of numbers and I wanted to double them, I could have a function called double and do that. Or if I wanted to say times 3, if I had a function that took a number and returned it times 3, I could do that. I also have these little inline functions. They're called anonymous functions because they don't have a name. We need a little bit of programmed behavior to send into something. So I've got a number. I just want to turn each number that comes through to string. Now it also comes built in because, again, Highland, they've already thought a lot of these problems and usually have answers for them most of the time. There's something called Intersperse where I can put things in between each item inside the stream. So I want to turn each number into a string, which means I can get rid of this up here and just continue working with numbers like I was before. And I want to put a new line in between each of them, and then I want to send the whole thing standard out as a string. And that works. So even though we've introduced streams, I started it with fitting everything in memory. Does this mean now, though, that like streams, we still run out of memory? Well, we can do bigger numbers, and it seems to work fine. We can even do, I could do that same like billion thing, and it would just take forever. But just to prove that it works, I'm going to go ahead and cancel that halfway through. So it went to infinity. What happened was Node ran out of its ability to represent big numbers before we ran out of memory. So that's a problem. We could solve that one, but that's not what this is about. This is, I didn't have to put everything in one place before processing it. And in this case, the processing that we're doing is printing numbers. And in this case, Node ran out of numbers before it ran out of space, right? Again, there's ways to solve that, but it means that we solved our initial fitting everything in memory problem. So this section is called Can Streams Talk, which is to say, great, so your program can spit out a bunch of numbers, but what if I don't want a bunch of numbers? Well, I mentioned to you that Linux and Unix has this already built in. So if I were to say, there's a program called Echo that will say hello, and that will print out a word. What if I wanted to know how many letters are in that? Well, there's word count. You see character. There's 6 letters in that. So what I want to draw your attention to is this little symbol here. This is called pipe. So Echo is a program, and it emits data to, by default, standard out. So Echo responds or sends data by default to standard out. And word count reads from standard in and does something with what it found. So if I want to say how many lines were in the input, there's only one line in the input. Right? If I wanted to count the number of lines, so there's a cat program. Let's see. Cat will, I could explain the history of why it's called cat, but basically cat right now, for simplicity's sake, just prints out the contents of the file that you ask it. I could also pipe this file into word count and say how many lines are in that file, or how many characters in that file. What are some other things? I could sort this file, and now you can see my program sorted alphabetically, which makes no sense, but we could even pipe all that back into Node, and sure enough, it breaks right away. Right? So you can connect the output of one program to the input of another program and just glue things together that way. And that is a really powerful concept inside of Linux and inside of Unix. It's my kids. And you can leverage that inside of Node. And in fact, you can leverage that inside of any program that you write. If you start thinking of your program as a piece inside of that universe of connecting things into each other, then you too can leverage all of the power that exists inside of your computer. But if you when it starts to dawn on you that files too are streams, you can connect your programs to files as streams processors. Or when you think of web requests as streams, you write a response back where someone requests something in, right? And that request might come in with data that you might have to process. Well, you can think of those as stream problems too. I won't touch that today. We're just staying inside of our program and a little bit to the command line there. Okay. So what I want to be able to do is, even though my program emits more than 1 billion numbers, I don't want to read more than 1 billion numbers. So let's run again fib. Where is it? In here, in fib. So that prints out all my numbers. I just want the first 5. So that runs the first 5. And so it gives me the first 5, but there's an error there, epipe, error pipe. Basically, it's trying to tell me that there was an error event that I didn't handle. So why does it have that problem? Let's see, watch this. If I run a 10 item stream, and I just ask for 10 things, there's no error. And that's because my reader ended at the same time that my writer did. But if my reader, which is in this case head, stops asking for stuff prematurely, my program's mad because it still has more items to send, and I'm trying to send it to this destination, but the destination isn't listening anymore. So that means that my program is not paying attention to who's on the other side to consume. So we can make them talk, we can connect them. So what I would do then is process that standard out. In this case, my writable stream quit, right? So there is some things that we can do. So it emits events just as well. So let's see what events. So there's an error event that I didn't handle. Let's check it out. Let's just see. So this ... means I don't know how many arguments I'm going to get. Just stuff them all into args. And I just want to print out what comes through. So that's this console.log. Let's make this a little easier to read. Standard out error, and whatever the error is, and then we'll move on with our life. It didn't get anything, but it just means that that was handled. I don't know why I didn't get anything. It was supposed to. But now it's not complaining, so that's good. What was supposed to happen, though, is that it was supposed to tell me that... actually, let's see if I... How can I trigger this? Maximum call stack size exceeded. Now we're going to go back into debugging again. Well, I think the point is that the out already has an error, and then I'm trying to write to it again. But the point is that handling that error is what makes this problem go away. So I want to be able to tell my stream to stop trying to write, and that is where I would call stream, and it has a destroy method on it. Destroy means nobody's listening, just stop. And that makes it go away. So now I can consume less than my stream actually produces. So in this case, let's come back to that giant number. That's 1 million. That's more than 1 million. And it doesn't break. So that's an important aspect of this, right? So that's most of what I wanted to show, which is that you can connect these streams. So first off, you can model whatever problem you're dealing with as a stream. You can avoid having to put everything in one place or waiting for everything to arrive before you work on it. And you can connect your program to other programs, to the outside world, to whatever, as long as everybody speaks over this common concept called streams. Earlier in the video I said streams would exist as a concept whether you gave it a name or not. Streams exist regardless of what program you express those concepts in. This is how you express some of these in Node. Again, Highland is a really convenient way to work with them. I should at least draw your attention, there's other ways to work with streams as well, or to make streams. So for example, we had that generator that this was actually a useful way to think about modeling programs that generate data as they go. There is a function, this is available in the latest version of Node. I know it wasn't in Node 10, I'm using Node 12, no 10 here. Let's see if this works. So that means that I've got readable dot from. Where was it? Where's my gen? Fibgen. All right, so let's do readable from Fibgen. Yeah. Fibgen. Let's call that 10, I guess. And then let's pipe that to standard out. And again, this is going to give us that. Well, first off, it's going to get mad because Fibgen is producing numbers. Let's do this toString. But it's not going to put new lines between each one. So let's fix that. Let's see what happens if I run that Fibgen mix. Okay, it's not a function, but I have newer versions of Node, so let's use nvm use v12.5.0. I run the same thing again. It was close. So I got numbers, but it didn't complain. So that means that from is available for that. Well, the other thing that's nice is that Highland actually knows how to deal with, Highland also knows how to deal with generators. So rather than having to try to memorize how all this stuff works all the time, let's just copy this in. So Highland knows how to work with generators. Highland knows how to work with promises. Highland knows how to work with callbacks. And that's really powerful because that means that, like, if you've got some code that returns things from the database, and you can write that database query in such a way that it emits things row by row, you can deal with things object by object. If your generator rather can iterate or walk over all the results, you can treat them as a string. Excuse me. If what or how much you want to produce is dependent on a thing, you don't know it until something asked for it. So one way is, like, maybe if you have a program that generates text or generates random stories, and it says, I want 5 lines, I want 20 lines, I want 3 chapters worth, or a lorem ipsum generator, for example, you might not know how much you want. A generator could be a nice way to think of how to, like, keep walking and producing and spitting out numbers until the caller or the requester is done. We also showed then that the generators, or rather the, and we didn't solve that here in the generator. This is one of the downsides of using it this way, is if I just ask for 4 lines, oh, it seems to be fine. Oh, that's because I already handled process standard out. So you still have to handle these you still have to handle these errors of paying attention to what happens if your reader isn't paying attention, right? So the reason that this is fine is because we handled the fact that standard out stopped listening. So I'm trying to think if there's anything else I wanted to show you. Again, there's a lot of really good stuff in here. So there's the way to do readable stream. How about reader.from? There's also some, there we go, readable from. This is where you can learn to read about that. One of the things that we ended up doing is we implemented a transform stream without kind of realizing it. This isn't the only way to implement a transform stream, but the idea here is that we ran this stream, which is a stream of numbers, and we turned them into a stream of strings, and then we turned that into a stream of strings with new lines in between. So we're transforming the stream as we go. There's a way to do that without Highland, but Highland is much less painful. So then the last thing I wanted to show you is maybe connecting, data to a printer isn't the only thing you can do with streams, right? Like maybe you want to be able to just process the result and, I don't know, compute a single value. So we can still do that. So let's come down here and start from scratch. So let's make a new stream or a string. Let's bring this down so we can see it. So that's our stream. Actually, now that I think about it, this is going to break all this other code. So if you uncommented, that is, I want to try to publish just so you can play with it later. So I've got my stream, and that stream there is really big. Too big. Let's make it smaller. Let's do the first 100 numbers. Actually, that's another chance to show something cool about Highland. So there's more numbers than I want to deal with. I can take. Take is going to say, here's a stream. I only want the first 10 numbers. I can say that with take 10, right? So let's just add up the first 10 numbers so we can do something with them. So in other languages, you might have heard it as fold. In JavaScript, we think of it as reduce. If you're not a programmer, neither of those make sense. But what we want to be able to do is take a list of things, and instead of transforming each thing so that I map from one list of things to a transformed second list of things, if I want to take one list of things and turn it down into one value, that's called reduce, because I reduce them down to one number. So in Highland, we also have the notion of reduce. So reduce needs a starting point. So if I'm going to add things up, we start adding from 0. And then I take my total and each number in my list, and I just add up the total and the number. And that's going to run through the stream and build up a count as we go. So if I've got that, I need to be able to basically know when the stream is done and shoot out what the number is. So in this case, I've got, Highland does have a done method, but I actually want the results. So there's just one total, and then I'm going to console out what the total is. So that ought to work. Streams is not defined. We're on line 1015. Oh, I got something down here. Okay. Couldn't see because my dumb face is annoying. So that prints out 231. So if I change it to 15, it should print a different number. It's a bit bigger. It doesn't take long before Node can't fit that. There's a way to solve this, and maybe I'll let you play with this yourself, because Node has something called big num in it. So I can say a big number is 10n or a million n. I can also wrap numbers like this. And now big num is an implementation that knows how to deal with big nums. They just have to be wrapped in this special, special handler that deals with big numbers. So if you really want to play with this and figure out how to see if you can find the result of adding the first 10,000 Fibonacci numbers, you could use big num to help you do that. I'll let you play with that, see if that's something you can figure out. From here, basically this section, what I wanted to convey was, you can do things with streams and consume them and transform them and turn them into new values or turn them into new strings. You can take a stream of things that are synchronous, which is to say they're here right now and you don't have to wait for them, and turn them into things that you do have to wait for. And you can work with streams in all these different ways, and they're really powerful. But it really comes back to the very, very simple concept that a stream is something that is a sequence that is linear, that you can reasonably semantically work on it bit by bit before waiting for the whole thing to show up. And streams are also important because you can connect them together. You can connect them to transformers, and you can connect them to destinations. And those destinations don't have to live inside your program. They don't have to live on your computer. And I think in subsequent videos, if that's something of interest, I'd love to show you how streams show up in HTTP, web servers, how they work with files. I'd love to be able to show you how you can use streams and thinking in streams on your command line and replace things like Excel, replace things like, if you've ever had to use an online database sheet or spreadsheet to automate certain tasks. All this stuff lives on your computer or is a simple download away, and you don't have to do that. But it really leverages thinking about little small tools that can be glued back together. And if you do more reading, you'll realize that this concept is already known as the Unix philosophy, and that's something you can go read about. It's very beautiful. Streams are a big part of it. It's something that really excites me and has really changed the way that I've thought about programming. I was initially inspired to learn it because I had to work on files that were too big to fit into one program. And it had that same issue that we saw up here when I tried to print out a giant list of Fibonacci numbers. I had to process a CSV and it wouldn't fit in my program. So I had to learn how to stream. And then I had to learn how to handle it when my program produced more data than the computer can handle at once. So I had to learn how to stream. And when I was doing web requests where all of the data that would be sent across the wire was too big to handle and like my server would crash because I'd run out of memory, I had to learn how to deal with streams. So it's a really powerful idea. It's something I want to be able to share with you. And hopefully, you know, despite my kids and all the racket, it's something you'd be wanting to listen to later. So thanks for sticking around if you did this far. Talk to you later.